In section 16.3, we're going to review the Friedel-Crafts alkylation reaction. The first reaction that we're going to deal with is the alkylation. So the general reaction here is we can take a benzene ring and it can have substituents on it. Let me not use X. So we're going to use that for halides here in a minute. Y. Okay, substituents Y. This will be subject to all of the directing group effects, but also some other significant scope and limitations issues, so it's going to become important. This is reacted with an alkyl halide and aluminum trichloride. Okay, AlCl3. Aluminum trichloride is a strong Lewis acid. Okay, so that's going to get us into Lewis acid, Lewis base interactions, and we'll look at those when we get to the mechanism. This then produces a product Now I'm going to draw a line from the center and put the R group here. Okay, now this is a generalized or generic way in order to illustrate that the R group adds around the ring. It could add ortho, it could add meta, or it could add para. So this is a simplified way for me to illustrate that perhaps all three, or depending on the Y group, you get, of course, different majority products in those cases. Now, the scope and limitations of this reaction are pretty severe. And I wanted to take up this reaction after we talked about the directing group effects, activators and deactivators. So, scope and limitations. This is what we're always worried about for a reaction. Does it work for everything? What does it not work for? What does it work extremely well for? And the limitations here are when Y equals a meta deactivator. Do you remember those meta deactivators? Hit pause and make a list of them real fast. Okay, remember those? Those are things like where Y equals NR3 plus NO2, the nitro group, SO3H, the sulfonic acid group, and of course the rest of those meta deactivatings. That is the meta directing. Maybe I'll write that in. The meta directing deactivators. Okay? There's no reaction. Those rings are too deactivated for the benzene to act as a nucleophile in this reaction. Now, there's another group of Y at the opposite end of the spectrum. So you see, this is actually both ends of our reactivity spectrum. The functional groups that deactivate the ring very strongly, the meta-directing deactivators. And then, if the substituent is an amine, okay? R can, in this case here, equal H or alkyl groups, so that you have an amine group. Not an amide. Can you draw the difference? Hit pause and draw a difference between an amine and an amide real fast. Okay, to continue, again, there's no reaction. Whereas for the meta-directors, the benzene ring is too deactivated. Could the ring be too activated by the amino groups? Remember, the amino groups are the strongest activating groups that we have? Well, no. Remember our catalyst in this reaction? What was the catalyst? Aluminum trichloride. It is a what kind of acid? Right, this is a Lewis acid. A Lewis acid. Amines. Remember the definition of a Lewis acid? Electron pair acceptor, so it's electron deficient. A Lewis base is defined as what? Hit pause and can you define it? It's a lone pair donor. There's the lone pair on the amine. So of course if we have an amine, and I'll just make it a simple one here, plus, I'm going to draw aluminum trichloride out for you. Remember aluminum trichloride, aluminum only has 6 electrons. It's electron deficient. And so this lone pair will strongly coordinate to that. And of course this then becomes, with the aluminum trichloride on it, minus, plus, it has a plus charge like the ammonium ion. So in fact, we have to remember these basic fundamental reactions to be able to see cross reactivity in these systems.